Alright, well, thank you for the honour and privilege of speaking to you all today. It's been very, well, I guess I could say I'm very nervous, a lot of adrenaline for coming to speak to you guys, because I know that a lot of you are very talented, very intelligent people and have built some amazing products. And when I found out I was speaking last, I was like, oh, that's a bit kind of shit, because I mean, on the plus side, I got until the last minute to finish my slides, which is kind of cool, but on the downside, everyone else has already covered all my material, so I am feeling like, what value am I going to add to your conference experience? So I'd like to present to you Prometheus, yet another effing stream processor. That's cheap, but you know, there we have it. So Prometheus, a practical guide to living at scale. We are hiring. I'm not a Prometheus developer, so why am I here? Everyone else has represented their projects. I started monitoring. I was a very bad sysadmin when I was 20. You could say I was a cowboy. My friend who had hired me to do that did say that. After I left university, I went straight into system administration and thought that monitoring is probably a good idea. So we deployed our first Arduino installation. A couple of years later, a bunch of friends and I decided that we were going to write our own. It was going to be amazing. We had great user stories like getting paid at 3 a.m. and racing into the data center on motorbikes and having automatic analysis show us the root cause by the time we got in there, so that we could fix it. It was mostly about the motorcycles, but we did get some visualizations going, and most of the time spent over engineering our DOM to represent what a network looked like. But the other day I was very excited to see the Sysdig Cloud talk, because that looks pretty awesome, and kind of what the dream was. So a bunch of other stuff happened. I got hired by Google, and then I stopped doing open source work for a very long time. I still worked with monitoring infrastructure there. Tony talked about some of the stuff that we use, so I was using Google for a while, and then it took many years of trying to wrap my head around the paradigm shifts, but then I learned how Borgmon worked. And I started dropping hints to my friends in the open source community about how this works, without trying to talk too much about the specific design of things or how they fit together, but just kind of time series, you know, collect it, do some maths, and see what happens. And nothing really happened for a while, but then eventually I got the chance to speak at PuppetConf 3 years ago, and I just wanted to kind of lay it out and say, this is what I'm really trying to talk about. So there's the idea that Nigis is not very great, and people are talking about monitoring sucks about this time, and I thought, well, I know that monitoring doesn't have to suck, so I think I should talk about it. But the problem with that talk was the technology I wanted to demonstrate, I couldn't. And so I left that conference feeling like I let everyone down, because even though everyone said that was kind of a good talk, they didn't have anything that they could go home and hold in their hands and build stuff with. I did say I was hoping by presenting that talk that someone would build something, and I guess from my previous slide, now it's called for choice. I'm not saying it's my influence, but you know, it is nice to be in a world where there is more than 0 options to perform a demonstration with. So why Prometheus specifically? Prometheus was written first by an ex-Google engineer who missed Borgmon so much that he wanted to have it again. Then he went to work at SoundCloud. SoundCloud started integrating in the infrastructure, more Google SREs started piling on. Sorry, ex-Google SREs started piling on. And not necessarily SREs, sorry. I don't actually know that for a fact, they're just ex-Google engineers. And so now they run this project, and it's going really well. So when that was announced earlier this year from the SoundCloud blog, and I was very excited that I could come back and do the same talk with actual demos that you can totally use. Having no idea, of course, that everyone else had built all the same things. So, things I'm going to talk about, and I want to warn you beforehand that this might upset you. Maths, everyone always said to me in high school, well, everyone around me was saying in high school, teacher, what good is math anyway? And I'll tell you now the answer is being paid a lot of money. everyone at the conference has done me great service. Sorry to talk about this. I'm not going to present too much new material, but I'm lazy, so the slides are still there. I'll just skip them really quick, and if I've got some little annotation I want to add, I might do that. I'm repeating a lot of material from the PuppetConf talk. I think it was the good bits. I think it's the stuff that's going to try and emphasize the point of what I'm talking about. I know that some of you were there, and I'm sorry. And to the ex-Googlers in the crowd, and the ones especially on the live feed, I'm really sorry. This is going to trigger some post-traumatic stress disorder. But it's okay, I've talked to the AV guys, and they are going to put in some subliminal message streams into the live video feed. So as soon as I start talking about Borg 1, the screen will go black, and you'll just hear a hissing noise. You'll pass out, but no harm will come to you. And so with that, let's start the talk. And that, ladies and gentlemen, is how Prometheus works. And I would like to thank you for giving me the opportunity, but I think we're out of time, so there's no time for questions. Okay, so obviously that's a joke. I'm very glad it went well. Tony hinted about this yesterday. The white box is metrics collecting, and we get to introspect the state of the system. And black box, we don't get to understand the internal state. We treat it as a black box, obviously, hence the name. We interact with it through the API that the service exposes. So we're pretending to be a user interacting with the system. Nagios historically was a black box service. It knew how to speak HTTP to a web server. It knew how to ping hosts. It was generally, and I know I'm overgeneralizing at this point, it was used to test to see if things were up and responding in a way that a user might expect to see that. So Nagios is just periodic scheduler. When I started talking about this, I called it the service called N, and I'm not going to give it a name, but I realize now that we moved on from that and everyone doesn't like it, so I didn't want to hurt anyone's feelings then, and I'm not fussed about anyone's feelings now. So I will call it by name. Nagios is just a periodic scheduler though. It runs external programs. It doesn't really do any of the checking itself, but it knows how to run programs and take the results of those checks. The configuration, describes the target and the check pairs by manually constructing a full cross product of what to test on which machines. The time series database was added as kind of an afterthought through the perf data system. I think I'll skip some of this stuff because obviously you guys know about this stuff. I highlighted some of the bottlenecks with this system though. Obviously forking a lot of processes to run a lot of tests doesn't scale very well, and I'm sure a lot of you people have been in a situation where you're running a Nagios system that was running out of resources to run a lot of processes. The other thing that I found really interesting when I was at Google was that I didn't realize at the time, but the configuration complexity was also a killer in human time. And we'd write stuff like code generators to work around this. So we wouldn't have to write all of the Nagios config, we'd write something that knew what a web server had and which of our machines were web servers, and then it would just do a mail merge and spit out a thing and send off Nagios and say, please do a thing. So how do you make Nagios scale? Or how do you make the process of checking things and collecting the data and deciding whether or not a thing has passed or failed scale? Obviously the answer is you build a time series database, you do advanced metrics processing, blah, 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 blah. We've seen it all before. So the context I want to talk about this was, we recently published this paper about Borg, and we talked about a whole lot of stuff about our grid computer, and Tony totally covered a bunch of this stuff too. Borg 1 is basically a mixing desk. It takes in the signals, you program a bunch of effects, and it generates new ones, and cool stuff happens. The important stuff that I like about it, and I think the stuff that people dismiss when they're talking about the PTSD, is the fact that it's a programmable calculator that allows us to be very flexible and abstract away the problem of determining what to monitor and how from what the kind of descriptions of the services we want to monitor is. Borg 1 is not, and I assert that the other time series processing ones probably are not, even though I haven't used them, but they all look the same, so they must be the same. System profilers, exception catches, load testing, load processors. I think those things are all great, and they should be work in parallel together. And I can imagine the thing that Brendan Gregg was asking for would look like a UI widget on top of all of these systems that would know to say, oh, like, I'm going to go to my profile collector and say, build my flame graphs out of that, or go to my log processing framework and extract things, events that happen about the same time, and try and correlate it through that stuff. But let's talk about how it works. Borgmon and Prometheus are both pull. There's an export proxy for both of these systems that can take push metrics and export them in a proxy format to both things. I think push is a conspiracy of vendors who just want to make it easy to get metrics to your firewalls. In the end, it doesn't really matter which one you choose, and I feel like taking sides doesn't really matter. That's also been talked about, so I don't need to say any more on that either. So Borgmon basically runs in a loop, and it's every duty cycle starts rule evaluation and scrapes a bunch of targets, and it offsets the scrapes so that it's evening load on itself and across all the members within a single job in a cluster. So it looks like this. There's a user, there's a browser, Borgmon, scraping bars from one task. If we want to add multiple targets, we do it like this. The way Borgmon finds targets, so the way Prometheus, I'm going to keep saying Borgmon, and I mean Prometheus, because they are the same, just like all the other ones. BNS is the Borg name service, which is described in the paper I linked to earlier. It is, as Jeremy talked about earlier, a service discovery framework. Basically, you give it a name in BNS path thingy, and it spits back a list of host port pairs. So it's like DNS, except it handles the fact that tasks move around in the cluster. So, your little container is running on a machine, Kubernetes decides that it's going to go somewhere else, chucks it over there. Then the container manager on Borg, called the Borglet, then updates the zookeeper address, the chubby address, to say this particular task is now in this location. So we want to add alert notifications. Sony called the Borg alert. It manages the rules on how and when to send notifications. It's kind of more of a log stashy grok format of pattern matching. So it pulls in the labels from the alerting rule and then looks through a bunch of filters to say what ones does match, and then that tells me what action to take. I think the escalator, sort of in the pinkish circular box, is pronounced PagerDuty to you guys. And what else? You add long-term storage, you stick it in time series database, obviously, and you want to do global monitoring, so you run another Borg one that looks at all the other Borg ones and scrapes all the data out of it, and that uses a different protocol, a pure protobuf-based API. And then sometimes your service gets too big and you're like, oh no, my data center level Borg ones are overloaded in either RAM or CPU. So we try and run these things with about 12 hours history. That's kind of rule of the thumb. But so that we can use them for exploration after we get paged, we can poke around in charts and stuff. But there's a lot of time series, and 12 hours of data doesn't, it's not small. So sometimes a Borg one might boom. So to fix that, teams tend to drop in shards. This is a common Google technique for scaling things. Shard up the stuff, defer it to other workers. Pro tip, if you are going through a Google interview, you can use the phrase, I use some shards, and that will pass the interview. Okay, so we've got a framework for running these things, but what I really wanted to cover in this talk is how do you actually write alerting frameworks. We've had a lot of people talk about that they can do this, and they've given examples of how you would do that, but at the end of this, I would like to show you this actually running and some concrete examples of how you write this. So I've got a small bit on alert design, and a lot of people have been beating around the edges of this. So James Turnbull showed us a slide about the relative importance of tiers of situational awareness, starting at business intelligence at the top and working his way down to the infrastructure at the bottom. And I think this is totally the right way to do it. And it's a guide to the methodology of coming up with good alerts to page you to let you know that the service is or is not working, well, page you that it's not working, right? Melanie in the lightning talks talked about this methodology as her DCVA loop. And Roy referred to it in his first talk the second talk, about doing what works for you when he was talking about how to minimize the number of metrics required, you start at the top and define what the alerts you want are, and it's very easy to funnel that back to the thing and define what the metrics that should be collected are. And in the Strike talk from Daniel, Dan, and Franklin, they talked about how they discovered the lack of coverage of one of the services they had expected to page when a fault occurred. Good alert design methodology should help you prevent this situation, but I'm not going to say it will solve this permanently because obviously bugs happen all the time. You can think of a game day as like a coverage test for making sure you have good alert coverage and help you to identify and feed that back into a review and another process of making alerts that you want. So we have this concept of service level agreements, and there are two feeder components under that. The SLO, the service level objective, which defines the goal that the SLA is trying to, so the SLA is the economic incentive, right? You have an agreement with somebody else that you're going to provide service at some cost to you or to them. The goal you want to meet, the goal you agree on without the economic carrot and stick is what the SLO is. The SLI, the service level indicator, is the service level objective without the goal. It's the thing that you're going to measure that's going to tell you whether or not you're going to meet that. So this is very easy to say, obviously the SLI is a metric or some aggregate metric. The SLO is some metric compared to something, and SLAs, I don't know, business people. People build their services against your SLOs, because if you're going to provide some level of availability, then it's very easy to take that SLO and decide whether or not they need to perform cool tricks like Jeff Dean's reliable hold from unreliable parts. They can improve the reliability of their system even though your system has a lower SLO if they use certain techniques. And so it's possible to capacity plan what their service needs to be based on your provided SLO. So this is a very nice contract for dealing with other services. So how do you pick an SLO? The rules of thumb in SRE are generally that we get paged about 2 times per shift, which is about 6 hours debugging. We tend to be 2 teams follow the sun rotation, so 12 hours each. You spend about 6 hours trying to figure out approximate cause or multiple approximate causes to the alert, and then doing the obvious workaround, filing bugs, doing some triage, chasing up with software engineers, or applying a permanent fix to, depending on how long obviously the work takes. So we want to balance the amount of time we get paged so that we have enough time to fix the things. If you exceed the SLO too much, obviously you have less time to fix things. So if you start to feel like you're getting paged too often and you start to exceed this rule of thumb too often, then you can trade off the SLO against unplanned work by reducing your SLO and saying, we're going to be paged less often. This is a business decision we make so that we can free up time so that we can attack the known problems. And this is something that Gene Kim and et al. Talk about in the Phoenix projects. If you've read it, he talks about unplanned work and how that's disrupting all of the project work that's going on. When you're designing alerts, obviously there are a lot of things you might keep because you're like, oh, that really tells me that thing's the thing that's broken. And you can totally do that. Just don't make them page you. Stick them on a dashboard, and that way when you do get paged for something that's actually business critical, you can go to your dashboard and say, oh, I see, well, their line goes like that, and that thing's firing, so I'm going to start looking in this particular subsystem. Alerts don't need to use 1-second resolution metrics because the response time on an alert is in the order of minutes, and you can get high quality signals without having to spend so much resources on acquiring this and storing those high resolution metrics. Now I totally agree that 1-second resolution metrics are excellent for debugging because it helps you to infer cause and effects between time series. But I want to emphasize that alerting is not troubleshooting. Alerting is deferring all of the work of actually watching consoles to a computer to tell you that there is a problem that he's investigating and freeing you up to do other things. Troubleshooting obviously is in response to being alerted. So at that point you do want to have stuff that you can dig around in and let you know what's happening. But let me emphasize again, alerting is not about getting high resolution metrics. Alerting is just being able to tell you whether or not the service is performing to the SLO. So now that I've said all that about alert design, I'm going to throw all of that out the window and go from the ground up, build a metric, chuck it in the stream processor, and then make some alerts based on that, because I think this way around helps demonstrate the flow of data through the system and helps you to understand how to build this stuff. So a bit of history, Google servers were all HTTP based, kind of makes sense for a company that's based around the web. So we're just exporting variables out of a standard interface that started out as just a human readable thing, so someone could poke it in an individual server, and then gradually it formed into this machine readable format, and then it was standardized and said, okay, this is how we're going to machine read. It's still a plain text format, and it turns out that's really good because it's really easy to add this to all the languages. Now we have 4 main official languages, but there's probably like a dozen or more languages used: Ruby, Haskell, Shell, and if you want to export metrics in the system, it's really easy to do so if the barrier to entry is really low. So just collect a bunch of global variables and then every so often take a lock, write them out, and you're done. Go Xfile library is influenced by this design, but let's look at the Prometheus client API. Here's an example in using the Go client. That's it. You define a metric, you register it with the Prometheus client, and then you increment it every time you want to increment it. The metric handlers are also plain text. I don't know if this is influenced by Google, but let's just say it is. The metric handlers for Prometheus are a little bit more descriptive. There's a bit more metadata. It has some help text that can tell you why the metric is there. And if you look back at the previous one, we've got some help text that we can write in the code and say, the reason why I have this metric is for obvious reasons. And we have a type. We can say that things are counters or gauges or distributions or summaries. Distributions are just histograms. Actually, they're just called histograms. And summaries are like an inverted histogram. I store the quantiles and update quantiles magically, and I don't really understand them, so I'm not going to talk about them. So I already said that Prometheus is a programmable calculator, and it can derive arbitrary rates and other aggregates from total variables. It's much harder to do that from pre-computed values. So here's rules of thumb for making good metrics that are going to be easy to handle further down the pipeline. Non-monotonically increasing metrics can lead you blind to changes, and I might cover that later if we're not bored. You don't want to export strings. The short answer is because Prometheus doesn't do strings yet. The long answer is it's much easier to have the count of exceptions by exception being raised. If anyone can think of why. Prometheus knows the timestamp at which it collected the data, so you don't need to say the timestamp exists. Prometheus knows because it just queried it at that point. So you don't need to store last sync times either. You can say, how many times have I done that? And Prometheus will, as long as these are monotonically increasing counters, then Prometheus will know that the counter is changed at some point and it can attribute a timestamp to that. Okay, so let's talk about how we collect those metrics with Prometheus. Prometheus has one master config file written in YAML, and it refers to a bunch of rules that you add, which are written in the Prometheus rule language. The master config defines kind of globally stuff, like how often do I want to run the duty cycle, and what labels do I want to apply to every time series that comes into this particular Prometheus. Then you can say there's rule files, they look like this, and then there's a bunch of stuff about scrape config, which says how do I find the targets that I'm going to collect from. So you can manually list them by just writing them straight into the config, or you can use a generator to emit files from some service management database, and then you can import that using the files thing. Better yet, Prometheus can find out where the targets in your data center are dynamically. Jeremy talked about using Zookeeper, which is basically the same way BNS works. James Turnbull did mention that he said he thinks pool means the server needs to know where the targets are and have configuration management having rolled out where the servers really are, also push the monitoring config changes. And I'm going to say that service discovery makes that problem go away, so you don't have to have that as a reason to not do pool metrics. Static processing is probably best left for testing and so forth. There's a whole bunch of different dynamic things supported by Prometheus, like it knows how to speak to console, it knows how to speak to DNS serve records. There's a few others that obviously the slide is not too big. Documentation has a bunch. Okay, so the collection occurs, and The time series are read into one big payload. As the VASI arrives, they're decoded and written into the time series database in memory in Prometheus. This is the same duty cycle as what Bogwan has. There's less stuff, but it's not relevant why there's less. Kyle and Rob from Boson talked about this already. Kyle's slides were much better than mine. There's a big matrix of time series. There's time on one axis. There's a bunch of labels on another axis. Scrapes end up at the bottom, and like an append log, if you like. Every time errors is incremented, all the labels, all the hosts it's come from, go across, and we write a new line at the bottom. And because RAM is not infinite, somewhere at the top they fall off the edge and disappear. So Kyle described two axes for metrics, physical and logical, and I think that they're just attributes. So Prometheus doesn't differentiate the two, it just says they're tags. It's a bunch of labels with key and value pairs. So we can refer to anything in this multi-dimensional matrix, including the variable name itself. And so you can see there's like infinite time series with different names, and they have a bunch of labels attached to them, and they go back infinite in time. So streams of time series were... The data in Prometheus is immutable. Once it's recorded, you can't change it. I mean, that's kind of obvious, right? This is what the data point has. There's a name that describes it. The name is composed of label sets. Label sets are just key value pairs. And at the end of it, there's a value and a timestamp. Yeah, I think I'll cover some of that a bit later on. So the labels come from the physical attributes, like the location. There's logical attributes that come from the application itself, which can say things like which exception is slide or what error code I return. And you can additionally specify more labels in the monitoring config, and we saw one of that earlier where I said this Prometheus happens to be running in that US East zone. These are kind of more physical attributes as well, but it's talking about the aggregation topology of your monitoring infrastructure itself, which is really useful when you start aggregating at a global level and you want to know that some set of time series came from that availability zone, some came from over there, and at some level you want to differentiate the two, but at a global level then you want to pull them together. Okay, so how do time series look in Prometheus? This is an instant vector. It's the most recent instant of this vector of time series. We can specify partial sets to describe small subsets of, not small, but just subsets of the time series. And there's two ways you can describe that in the Prometheus language. The shorthand form is just to put the variable name at the start and then everything else. And this is kind of nice if you don't need anything else, you can just write it without all the curly braces. You can be all kinds of specific or inspecific as you like. If you specify all of the labels to identify a single time series, you get a single vector back, a single element vector back. And I think in this example, if you assume that this data was all that was in there, then you could have gotten the same result without specifying zones, since the other labels also uniquely identify this one. So I talked about types, so I don't think we need to cover this too much, right? Counters are always increasing, gauges increase and decrease over time, right? Counters are great because when you sample them, you still know what it looks like. Gauges are terrible because when you sample it, you don't know what it looks like. So we're 60 slides in, and I have no idea how much time is left, but we're at the meat of the talk now. So the rule evaluation. Recording rules is the data processing language of Prometheus. They compute and they store the results of query expressions, making them permanent. So in this example, we are computing for all the instances of requests on jobs labeled web, we want to compute the 10-second rate of change. So we want to look at the 10-second history. And this particular expression is called a range expression because it doesn't go across the labeled dimension, it goes across the time dimension. The left-hand side implicitly inherits all of the unspecified labels that result from the expression. So we've kept the instance label, we've kept the job label, we've kept... Yeah, just those ones. When you write a recording rule, this part is called the variable reference. This is the range expression. This is the function. And this is the recorded variable name. Now, it's got a funny notation. Both Google and Prometheus recommended naming practice is to stick the aggregation level in the first component, the operation that created the variable in the last component. And we can stick different operations in there. So we can say like the sum of requests using task request sum. We can say the 10-second delta of requests is 10-second delta. Right? Anyway, it makes it really easy to read. You can say, I'm looking for the task level variable of some particular thing and this particular operation that created it. So we've got a bunch of ways of specifying rules, and now there's two types of rules that we build. I think there's a little bit more, but I haven't been able to prove that. But I'm just going to say it's possible that there are. But the first one is aggregation based on topology. And the idea is that we know what our service looks like. We have to tell Prometheus what our service looks like. What is the aggregation layers? Do we have a job comprised of a whole bunch of tasks that run as a cluster, implementing a service in 1 or 2 data centers? So we want to say that there's that set of tasks, they aggregate to a job level, which is how we describe the whole cluster operating together. And then at a global level, we're going to say, well, this global service acts like this, so let's pull all those things together. We've got the prefix again saying what aggregation we're at, and the sum by operator says these are the labels by which you should fan out the computation. So we're going to retain the job and the zone, and all the ones that have the same job in the same zone will be summed together. And the output is going to be some matrix, some vector, sorry, of results. Actually, I think I'm just going to use vector and matrix interchangeably because I'm having trouble visualizing it. You can have the second type of rule is the relationship. And so we have variables at the same level that we can say that there's some schema associated with them. Borg1 doesn't care. Sorry, Prometheus doesn't really care. It knows about the types of the things, and it's probably, I think Prometheus will actually error check what functions you're applying to types of variables. But let's say it doesn't really matter. You're just going to compute sorry, let me backtrack. That was a bit of a going into the weeds there. If we want to say what's the ratio rate of errors to requests, that's kind of an obvious thing we want to look at. We know that there's a relationship between those two because one of them is coming in and one of them is going out. We can find out what the ratio is, and then we can understand something about a service. So at a particular aggregation level, we want to build relationships. We can add this on modifier to say that when you're doing the join, use this variable to describe how to match the two together. And if you have mismatched vectors, then one of them might have more labels than the other one, or it'll do the join and say, well, hang on, this one's giving me a single element result, and the other one's giving me a multiple element result. I don't know how to do that. You can say, well, if that happens, fan out by this label on one side and say, okay, for each one, by that label, do that. And if it turns out that it tries to do that and there's still too many, then you keep adding labels until somehow it magically works. But does that make sense? You want to say, I want to compute the ratio rate, but I want to keep the return code, the error code, as a result. And so I know what the ratio of internal server errors to requests was versus the 404s to requests. And then maybe at the end you sum them all together to get the overall error rate. Okay, so now we can build rules to build an aggregation that describes the topology of our service, and we can write schema rules that can talk about the relationship between our variables. What next? The actual talk. All right, so some real world examples. Is this going to work? Yes. Just some case studies I put together to try and help demonstrate. Oh no. Totally forgot to plug in the
Yeah, I'm Hardy's right. Yeah, let's drink some more beer. Yeah, hey, what about some beer? Yeah, Hardy's right.
All right, guys, pipe down.
Hey, hold on. I'm worried about the beer supply. After this case and the other case, there's only one case left. Yep.
Okay, that was the important part. Okay, so we want to alert when the beer supply is low. We write some mathematics to say how it should happen. In the condition that cases -1 minus 1 equals 1, the alert is true, and otherwise it's false. And how would you describe this in Prometheus? You want to say the function if cases -1 minus 1 equals 1, we want to alert Barney worried about beer supply. Sorry, this is very small on my screen. And we're going to alert with a summary that says Hey Homer, I'm worried about it this way. You can read it. You know what he says. This is a very, kind of a very familiar alert, right? It's just testing a single thing against a single threshold, and you can totally do that in Arduos. So what else? Disk full alerts. What do you want to do with a disk full alert? Do you want to take the absolute value of the disk and page when it hits a threshold? Or do you want to take a percentage of freeness and page when that hits a threshold? And that really sucks because disks are different sizes. One thing that really sucks about Arduos is that you can't say, solve the problem for me once and for all. You have to go and individually say, this particular machine has that size disks. And I think that barrier alone has prevented so many people from alerting on disk fullness situations. So a more general alert means it's scalable, right? Because you're not writing all those individual things. You don't have to think about alerting. What is it you care about when a disk is full? Is it that a disk is full? Probably yes. Okay, so you want a page on that. But how long does it take for somebody to fix a disk that is rapidly becoming full? Calculus. So I'm very sorry. Okay, so how do you alert on rates of change in Prometheus? I mean, I guess people already understand because we've seen a lot of effects processes.
Quiz, hotshot. There's a bomb on a bus. Once the bus goes 50 miles an hour, the bomb is armed. If it drops below 50, it blows up. What do you do? What do you do?
Right. Serious business, being on call. Okay, so let's say the alert latch is true once set, so the second half works. I'm just going to try and poetic license that one. How do we compute Dennis Hopper's alert? He wants to know that the bus has already gone above 50 miles an hour, and then it goes below 50 miles an hour. So, alert, the bomb is armed, the speed has gone up over 50 miles an hour. And then do something that makes the bomb explode if, this is how you write it in Prometheus, because you can look at the history of the thing that it alerted already using the alerts time series. And so it's got the alert name as one of the labels, and the alert state is firing, and it has fired at least in the last day, and I'm going to say that probably the length of the film isn't going to last longer than a day, so this totally works. We're not going to have any accidental misfires or fails to fire. So Dennis Hopper is very happy right now because he's going through his dirt exercise, his game day exercise, and all the everything works. What does Keanu want to know though? First he wants to know what bus it is. So should he start saving the bus at the point at which the bus goes above 50 miles an hour? No. Keanu probably cares about how the bus is slowing down and approaching 50 miles an hour from the other direction. It's because it doesn't matter how long it takes to save people as long as the bus is still going above 50 miles an hour. So we want to know what point does the rescue operation become time critical. Obviously once to find the bus, right? Get the people off. But once the bus starts slowing down, that's when you know that you have a time limit to resolving this disaster. We don't care that acceleration is negative, we care that it's rapidly decelerating because that changes how much time we have to finish the rescue, right? So back to your high school calculus, you learn how to perform simple mathematics on physics, right? And you know that, whatever I wrote, you know that that's true, right? So we can say that if, obviously just translate it straight into a Prometheus. So yes, boom. I want to know what bus it is. Wow, that was quick. I was not expecting to come to demo, so I'm going to give you a demo. This is going to go extremely well. It was going to go extremely well. So I said that. Okay, so let's... Okay. Let's see if this works in 5 minutes then. Luckily we're not dealing with that situation anymore. Okay, so I have a crappy web server. So that's my load balancer. I have a crappy web server. The web server exports the metrics. That's not crappy. The crappiness is that it fails a bunch of times. It takes some time. The back ends also are slow, but we're reporting back end latency, and every so often we fail, so we record that error. And this is going to be on GitHub, so whoever took the photograph, I'm sorry for moving it in the middle of the shutter. Anyway, we set it up and we run it. So the load balancer is also crap. It has a list of backends. It registers the metrics with Prometheus client. So it, it receives a request for whatever it is. It invokes the handler. It says, all right, time to start. It does a bunch of things. It tries to request a client thing, and if it fails, then it records an error. If it succeeds, it just writes the thing back. If the response encodes an error, then it passes the error back. And yeah, obviously it just records the thing. So it's actually a really brilliant load balancer. Yes, we got Prometheus running. I'll just start it again. So, I don't know where I am. Let me start again. Shit. So I have a little shell script that launches Prometheus with all the flags I need. And then I have the servers. Start them again. And I have yeah, so it couldn't connect to it for a bit, and then it could. So maybe I should kill them off, and let's go to Prometheus, and we can see that he's scraping some targets. And this is very hard. Okay, so a bunch of things are unhealthy, which is cool, right? It tries to scrape some targets, and it knows that they're not there. So let's run them. Yeah. Oh, that will be great. So I have a script that just generates a baseline load. It tries to keep 100 concurrent requests open for a long time, longer than the demo is going to run. And we can go back to Prometheus and we can look at our rules. And what I should do is show you those rules. So we've got a bunch of rules that describe task health. So we're just taking there's a synthetic variable called up that gets created by Prometheus every time it successfully scrapes a target. So it says up worked, yes, 1. No, it didn't work, 0. So we can say the percentage of, I'm gonna have to go look at this. The ratio of jobs within the task, we know how long the task is because we know how many variables are in the thing, that's the count. And we know how many are currently up because that's the sum. Because when you sum zeros and ones together, you're gonna get ones. And we can say the task missing alert will fire if 90% of the jobs are up. If 10% or more of the jobs are down, then it will fire the alert. It's going to be severity info because that's the way I'm going to say this is something I want to know about if I get paged for something else, but I don't actually care if 90% of the jobs are down. At least I don't want to be woken up if 90% of the jobs are down. Again, we can say task resets are how many times did the up variable reset in the last 10 seconds? And if that value for all the job exceeds 3 in the last minute, then we want to send another alert. And again, that's something that's probably really interesting for diagnostics, but not something you want to get paid for. So errors, we have, this is something I showed on the slides already. We just want to, the end of it is obviously alert, which you've seen in the examples, in the case studies. If the error ratio exceeds 20%, then we're going to page somebody about it. And it's going to send a bunch of cool text that says what happened. And finally, the latency loading is a little bit more complicated. We're going to use the histograms, and we're going to say, oh, I better scroll up. So the histogram exports all of the buckets of the histogram as individual counters. So we can say compute the rate of change, all of those buckets as just a simple rate computation, and it will do the right thing. It will keep the bucket labels on the other hand, on the left-hand side. And the latency count happens to correlate with the request variable we're also exporting because it just happens to contain the count of everything that ever went into the histogram. So if you're updating the latency metric every time you get a request, obviously the request variable is the same. But for clarity, I wanted to use this one instead of the other one. And I guess in reverse, I wanted to use requests, so I didn't confuse you about that. Yeah. So we sum them up and we compute the job total buckets rate and the job total count. And then we can compute the ratio rate of everything that was less than or equal to 250 milliseconds and over the total count. And you saw how this worked already with the errors. So now we understand percentage of requests that were less than or equal to 250 milliseconds in length of run duration. And then we want to say that our response time, SLO, is 5.9, so page if we drop below that. And that's it, right? AppDex was, I never heard about it before until I read the Prometheus docs on Monday, and then Kyle talked about it. I'm like, wow, this is a thing. You can do that. I don't think you should, but you can totally do that. I could show you the YAML file, but you can look at it at GitHub later. I guess we're running short on time. So I should show you that we are, well, I'm not getting paid right now. Oh, there's a, yeah, you can look at the alerts and we can see that none of them are failing. So let's back around that. And kill 771. Oops. Yeah, boom. Now the load balancer is having a fit. And if we do that, come on, there we go. Error ratio is too high on what the, I think that says it's this load balancing one. And if I click on here, and I reload it, I will learn that I didn't start the alert manager. That's cool. Damn it, man. There we go. Right, alert manager running. Set one notifications, boom. So yeah, we've got an alert and we can click back to the graph. Wait, what? I'm not really sure what that is. I'm going to say that it's this thing. So if I click on that. Right now, because I'm on localhost and it's doing some weird stuff, if I click on the alert manager one, it won't take us back to the right place. But I can open that up where it takes us here. We can see, here's the graph. Wow, that's way too long. 1 minute. Full res. Okay, so cool. We can see that the error rate is over 20%, and that's why we're being paged. Great. Let's fix it. Service. Stop. Oh, nope. Go around. Ah! Man, I totally tempted the gods, didn't I? They're paying, I'm paying for it. Yeah. How many things do I have to do? All that stuff. Oh, Chrome, yeah. All right. 1805. I hope I typed that right, didn't I? Great. Oh, again. Great. Okay. Let's start off again. Okay, let me begin. Alert manager conf. I want to. Alright, so alert manager can send alerts for a whole bunch of cool stuff. I'm not really going to talk about that. I'm just going to use it to make sure that we can send alerts. Can I get like 2 more minutes? Yeah, so alert manager is not really production ready. But okay, and last thing was start the load test up again. We're going to run a nice load test again. And I also have an antagonistic load test. So it's just going to send an awful amount of traffic. It's going to try and ramp up in a triangle pattern as much, like it's going to keep running Apache benches. This is That's all it does. It's not very nice, but that's kind of the point. So we should go back here and have a look at what alerts are firing. Nothing yet. All right, we can go back to the main page and we can scroll down and see our rules. Wow, things are not going well. There we go. It's going. Yeah, latency too high. Great. Okay, so you can see how we can obviously induce failure in our system, and we can totally be alerted about it. Great. Demo win. The last question is: did the Slack channel actually get? Yeah, it did. But the channel thing didn't set up any embedded pages, so I assume that means nobody's actually in the channel talking about this. So that's either great because you're listening to me, or really bad because you have just tuned out. Anyway, that's it. That's Prometheus. This is how you do alerting on time series data practically. I really hope that everyone who isn't currently doing this, so everyone who is smaller than Netflix and Etsy, and I don't know what the tail looks like, but I know there's a lot of people who are coming here to learn how to build this stuff and do Netflix style monitoring without spending as much money as Netflix does. So I really hope that that was useful, and thanks a lot for having me. We're totally over time, so there's no time for questions, but let's go after somewhere and you can talk to me. Or you can ask questions in the Slack channel, I'll answer that too. Thanks very much.